In this section, we'll look at how to use algebraic operations to combine simpler functions that allow us to describe more complicated situations. One of my simple functions will be revenue. If I sell X bear claws and each one costs 80 cents, then I can model the revenue as 0.8 times X. For each one of the bear claws that we sell, there's an associated cost for actually producing it. Suppose the cost for making X bear claws is given by this C of X function. Suppose we've determined that this model is only valid on the interval 0 to 1,000. That means if we ask about the cost of more than 1,000 bear claws, this model may not give reliable information. Here are the graphs of our two models. The line is the revenue function, which increases at a constant rate. The cost function in red also increases, but it begins to taper off as we get closer to 1,000. This is good news for us if we own the donut shop, because each bear claw we sell earns us the same 80 cents, but the bear claws become cheaper and cheaper to produce as we get closer to 1,000. Maybe we can get some wholesale prices on ingredients, or we can fill a larger oven, which is more efficient. We can come up with lots of reasons why the first bear claws may be expensive to produce, while the later ones become cheaper to produce. We have a function for revenue, and we have a function for cost. How can we combine these two functions to describe the profit for producing and then selling X bear claws? Profit is defined to be the difference between the money you receive from the customer, which is your revenue, minus the cost of creating the product, which is our cost function. We can substitute these names with the definitions of the function that we came up with, and then we can combine like terms to have a function that's easier to look at. This last line is a function that directly describes the profit of selling X bear claws. On these axes, I have the revenue and the cost functions like before, and I have a third function, which is the profit. So notice at the far left of the graph, when cost exceeds revenue, the profit is negative, which agrees with our intuition. If we're spending more money than we're making, then we have a negative profit. At a little over 100 bear claws, the cost and the revenue functions intersect, and that means we're making exactly as much money as we're spending. At that same number of bear claws, the profit function is equal to 0. To the right of that, our revenue exceeds our cost, and our profit is positive. Not only is our profit positive, but it's increasing as we produce more bear claws. This goes back to our observation that the revenue function increases at the same rate throughout, while the cost function starts to taper off near 1,000 bear claws. So if we look at 200 bear claws, where revenue barely exceeds cost, we have a very small profit. But if we look at 1,000 bear claws, where revenue greatly exceeds costs, we have a very large profit. What we've done in this example is take two existing functions and then combine them in a way that makes sense for our model to create a new function. In our example, we subtracted functions, but we could have chosen any of the usual algebraic operations. The sum of two functions, which is sometimes written as f plus g of x, is defined to be the sum of the two definitions of the function. In other words, we would write down the definition of f and write down the definition of g, and then add those two expressions. The difference of two functions is like the example we just saw. We write down the definition of the first function, write down the definition of the second function, and then subtract the latter from the former. We could also talk about the product, in which case we would multiply the two expressions, or the quotient, where we would divide one expression by the other. Just to have another example, let's say that f of x is the square root of x, and g of x is x plus 1. The product of these two functions is by definition the expression that represents f times the expression that represents g. F of x is the square root of x, and g of x is x plus 1, and we multiply these two expressions together. There's not a lot we can do to simplify this, so we'll just leave it as is. The domain of this new function is all non-negative real numbers. Even though the domain of g of x by itself would be all real numbers, the domain of f of x restricts the domain of this new product. We can't evaluate f times g at something like -1, because even though -1 plus 1 makes sense, the square root of -1 would not make sense, and that makes the entire expression worthless. If instead we wanted to look at g divided by f, the definition of that is g of x divided by f of x. So we would substitute the definition of g of x and the definition of f of x in the appropriate places. The domain of this expression is now all positive real numbers, so we've also thrown out 0. We can't use any negative numbers because of the square root of x, and we also can't use 0 because the result would be 1 divided by 0, which is also meaningless. The point of looking at the domain in these examples, the domain of the new function you've made may not be the domain of either of the two original functions, and so you need to look carefully at the model you've made.